Okay, class, I wanted to do an example, one more example of orthogonalization, and also a spectral decomposition, because I didn't walk through the one in the notes. Well, I pretty much walked through it. The work was written down, but I thought we'd do one. I'd work one from scratch. So, well, just a reminder, the spectral decomposition is a way of writing down a matrix having to do if, and this only deals with real symmetric matrices, but if it's real and symmetric, then we can write it down in a special way, and that special way is the eigenvalues times this this product of the orthonormal vectors corresponding to each of the eigenvalues, but it's an outer product that'll give us a rank 1 matrix. So we get these n special matrices that we can add up to get A. So it's a different way of writing out the matrix. So let's go here to OneNote. So our first task is let's orthogonally diagonalize A, and then we're going to find the spectral decomposition of A. So first thing we need to do is, for both of those, to let's find the eigenvalues. So let's take 5 minus lambda 0, 0, 1 minus lambda 3, 1 minus lambda. Take the determinant. So we'll get 5 minus lambda times, so I can eliminate the row and column that it's in. Here it's nice, I can expand like that, use the top row to expand by, and I only have to worry about the 5 minus lambda times 1 minor. So so we'll get 1 minus lambda times 1 minus lambda minus 9. And I don't want to multiply all this out because I'm just going to end up factoring it down again. So really what I want to do is multiply that together and factor it down. So 5 minus lambda. Here I'm going to have 1 minus 2 lambda plus lambda squared minus 9. And that will be lambda squared minus 2 lambda minus 8. So here I need, what are the factors of a negative 8 that add to a negative 2? Well, negative 4 and 2. So lambda minus 4 and lambda plus 2. So so a negative 5, 5 So if I have lambda equals 5, lambda equals 4, and lambda equals a negative 2, those are my eigenvalues. So now we need to find the eigenspace for each of these. So find the eigenvector for each of these. I know there will be 1 for each one of them because it's a 3 by 3 matrix and I have 3 distinct eigenvalues. So let's start with 5. So 5 minus 5, 0, 0. 1 minus 5, 0, 3, 0, 3, 1 minus 5. And I'm going to set that, augment that with 0. So find the null space of this matrix. I get 0, 0, 0, 0, a minus 4, 3, 0, 3, a minus 4, and 0, 0, 0. So I'm going to move that row of zeros down to the bottom. I can change that second row, divide by a negative 4, so I get 0, 1, and a negative 3/4. And if I row reduce, those I know are going to be 0. If I multiply that first row, this one, by a -3 and add to that one, then this first one will be 0, and the second one will not be 0. And well, the key thing is it won't be 0, and it also won't be a -3/4. So that means I can turn it into a 1 and eventually get rid of this. So, so this is as far as we can row reduce. That's great. Really, as soon as I saw that this matrix here, this 2x2 matrix here, as soon as it was, I could recognize that these are going to be linearly independent matrices. So, because a scalar multiple of 1 doesn't equal the other one that I know for sure, I can row reduce it to 1, 0, 0, 1. So, so what does this mean? That means x is a free variable, and that means, so x equals x, y equals 0, and z equals 0. So 1, 0, 0 will be an eigenvector for lambda equals 5. Okay, how about lambda equals, let's go lambda equals 4. Then we can take 5 minus 4, 1 minus 4, oops, that's 3. 3 and 1 minus 4. Augment with 0, 0, 0. Find the basis for the null space here. I'm going to get 1, 0, 0, 0. And here I get a -3, 3, 0, 3, a -3. And what's going to happen? Well, I can divide by a -3 to get 0, 1, 1, sorry, 0, 1, and a -1, and then I can use the 1 and the -1 to eliminate that bottom row. So that'll all be zeros. So this is what I end up with. That means z is a free variable here. So z equals z, y equals z, because that's y minus z equals 0, so y has to equal z, and x equals 0. So a basis for lambda equals 4, the eigenspace is the span of the vector 0, 1, 1. And for lambda equals a -2, 5 minus a -2, 0, 0, 0, 1 minus a -2, 3, 0, 3, 1 minus a -2, and augment with 0, 0, 0 to find out the null space of this new system, and that gives me 7, 0, 0, 3, 3, 0, 3, 3, and I can row reduce that. I can use the second row to get rid of the third row. I can turn the second row into 0, 1, 1. The first row I can turn into 1, 0, 0. So it's a really easy one. So similar to what we had before, except second row was a 1, 1 instead of 1, -1. Here we get z as a free variable, and x and y will equal a -z, because right now we have we have y plus z equals 0, so y equals the opposite of z. So that means I get z equals z, y equals a negative z, and x equals 0. So I get so for lambda equals a negative 2, I get 0, minus 1, and 1. Okay, so now I found the hard work of finding the eigenvalues and the corresponding eigenvectors. Since they are all distinct eigenvectors, I know that these will all be independent, but not only independent, since this is a real, since A is a real and symmetric matrix, so real and symmetric, then the eigenvalues are going to be they're going to be orthogonal. I think it's for any symmetric matrix they're orthogonal. If they're real and if it's real and symmetric, then they're real and orthogonal. So notice we do the dot product of this one. Let me change my color here. So if we dot product this one and this one, we're going to get 0. If we dot product the second and the third, we're going to get 0. And the first and the third, you still get 0. So they're all orthogonal. So what do we do from there? We're trying to orthogonally diagonalize A. So we need to turn these orthogonal matrices into an orthogonal vectors into an orthonormal basis. So we have to divide by the length to make sure they're length 1. That's easy. But first, just to make sure we'll get these straight, let me do 5, 4, and a negative 2 for my diagonal matrix. That'll give me an order I can keep my matrices, my vectors in. So let's pick Q. So my first column in Q has to correspond with the eigenvalue of 5. So 1, 0, 0, and the length of that is 1. And if I divide by 1, I just still get 1, 0, 0. That's a nice one. 1, 0, 0. So, okay, for 4, the length of this is the square root of 2. So I have to divide by the square root of 2. So 0 square root of 2 over 2, square root of 2 over 2. You could write it as 1 over the square root of 2 for each of those. That is just fine. And for a negative 2, so we're looking at the third column, it also has a length of the square root of 2. So divide by the square root of 2, you get 0, a negative square root of 2 over 2, square root of 2 over 2. So there's Q and D, so that means A equals Q D Q transpose. So A is 1, 0, 0, 0 square root of 2 over 2, negative square root of 2 over 2, square root of 2 over 2, square root of 2 over 2. That's Q. 5, 0, 0, 0, 1, 3, 0, 3, 1. Oh, made a mistake. I put down A instead of D. 4, 0, 0, minus 2. And then Q transpose. 1, 0, 0, 0, 0. That's going to be the same, but now we get square root of 2 over 2. Negative square root of 2 over 2 there. And these other ones are square root of 2 over 2. Okay. So now we've done A. We've orthogonally diagonalized A. Now, what about the spectral decomposition? So, spectral decomposition theorem says if A is real and symmetric, then, well, it might work for complex values too, but if it's real and symmetric, we don't have to worry about any imaginary or complex number showing up. It says we can rewrite A as the first eigenvalue times the first the first, it's supposed to be a Q. The eigenvector corresponding to the first eigenvalue, and then the eigenvector, that same eigenvector transpose, and then we can do that for each of the eigenvalues. Well, really each of the eigenvectors, you might have the same eigenvalue twice. And you might have to orthogonally, you might have to do Gram-Schmidt to make sure they're orthogonal if you have algebraic multiplicities greater than 1. So we can do this. So that means A, lambda 1 is 5. The corresponding vector for in the orthonormal basis is 1, 0, 0, so the transpose is 1, 0, 0. There. 4, the corresponding orthonormal is the square root of 2 over 2, square root of 2 over 2. So there's the orthonormal vector, transpose, and a negative 2 times 0, negative square root of 2 over 2, square root of 2 over 2, 0, negative square root of 2 over 2, positive. Come on, guy. Square root of 2 over 2. And then we can do these products, and no, this is not the kind of vector product that's going to get us a single value. This is going to get us a 3 by 3 matrix, and they're all going to be rank 1. So 1 times a 1, 1 times a 0, 1 times another 0. So it's going to be 1, 0, 0. And then we're going to have 0 times everything, 0, 0, 0, 0, 0, 0, all of that times 5, plus 4 times, here I'm going to have the first row will be 0, and then here I'll have the square root of 2 times all of those, so that's going to be 0, square root of 2 over 2 squared is a half, and again a half, and we're going to get the same thing because we're doing all the same products, and then minus, here I'll get the first row all zeros, second row I'm going to get halves, but some of them will be positive and some will be negative, so at least on these last, the lower 4, so a minus times a minus will be plus, so a half, negative a half, 0, a negative a half, and we can write that even a little more simple if we want by multiplying in the scalars, and they picked us some nice values for us, 5, 0, 0, 0, 0, 0, 0, 0, 0, and then here we have 0, 0, 0, 0, 2, 2, 0, 2, 2, and here we have 0, 0, 0, 0, 1, a minus 1, 0, a minus 1, 1. So this is the spectral decomposition of A. So we've written it out as the product of 3, since it's a 3 by 3 matrix, you can write it as the product of 3 rank 1 matrices. So all of them are symmetric. So there you go. So either of these should count, this first one or this second one. Okay, so we orthogonally diagonalized it, and we wrote the spectral decomposition. So hope that helps. Have a great day. Have a happy Thanksgiving. Well, maybe by the time some of you watch this, you'll have already had Thanksgiving. So I hope you had a great Thanksgiving. Thanks.